All right, my name is Brady, and I would like to try to design a pipelined CPU. So I kind of just want to get right into it. This is something that I've thought about for a long time, and I have some fairly developed ideas about the instruction set and the overall microarchitecture, but I don't want to go into too much detail there because it's just going to keep me from actually making the thing. Um, so we're just going to get started. I guess from a really high level, um, this is going to be a 16-bit processor. I want it to be pipelined. This will probably have something akin to like uh, a 5-stage risk pipeline. And if you know anything about the classic 5-stage risk pipeline, then you'll know that the first stage in that pipeline is fetching, which is where the processor uh, gets the next instruction to be executed from memory. So um, this processor is going to have 16-bit wide memory. So you're accessing up to 16 bits of memory at a time, but the memory is going to be byte addressed. So if there's a 16-bit address, that would be 128 kilobytes of memory in total if we just look at it from a simple standpoint right now. So what I'm going to do here right now is put together a program counter, which is that is not what I want to do. A program counter is a special register which contains the address where the next instruction to be executed is located at. And so that register is specifically this component here, and you can see I've made it 16 bits wide. And with the pipeline, typically you're going to be trying to fetch and execute, to fetch an instruction and complete the execution of another instruction every single cycle. So in effect, you're going to be incrementing this program counter to advance to the next address to get the next instruction every cycle. And because the memory words are 16 bits wide, but the memory is byte addressed, it means that basically every other address corresponds to kind of the base address of another instruction. And so after fetching an instruction every cycle, the program counter needs to be incremented by 2. And I'm actually going to cut that multiplexer out just so that I don't get too ahead of myself here. But that is exactly what this circuit is for. So I'm going to hook up this output here, connect it here. We'll say that it is, not 6 bits, but 16 bits wide. I'll get a clock. Eventually we'll have some more robust like clock logic here that's a little bit less manual, but for now we're just going to have this simple component here. And for now, let's say we'll just clock it at like 3 hertz for demonstration purposes. Now that idea of being able to fetch and complete the execution of an instruction every cycle is kind of idyllic. Like in reality, you're never going to hit that metric unless you have like multiple pipelines and you're doing like superscalar execution, stuff like that. But I'm not going to be doing any of that in this processor. So basically our goal is to try to get to as close to unity execution as possible. But later we'll run into things such as different pipeline hazards due to data dependencies and resource contention and things like that that's going to prevent us from ever actually hitting 1. But for now, we're going to pretend that that is not the case, and we're just going to enable this program counter register all the time, which is what I've done by connecting a 1 here. Yeah. So I just wanted to make sure that I had everything set up correctly. Let's just show decimal. Okay, so you'll see here now that the program counter, I think it actually is going to start up in a random state every time, which is something that we need to address eventually. But you'll see when I start the circuit again here that it's going to increment the value internally by 2 every time that it clocks. So it's going to increment by 2 3 times a second. Well, that doesn't look right. Oh, I'm stupid. I've hard-coded the carry input on this adder to be a 0 when, of course, it needs to be a 0. So it's an easy mistake, but that's cool. So this is kind of our proto fetch unit, work in progress. But now what we're going to do is we're going to try to connect a ROM. And this ROM is what's going to store instructions for execution. And you can think about the program counter as being an index into this big table full of instructions here. Let me enable this just all the time. And then this output here will be the instruction that has been fetched from memory. And the instruction is going to be 16 bits wide as well, just like the address. So we need to configure this ROM to say that it's got 16 data bits and 16 address bits, and we'll call this prog mem. And then I guess I'll pull this down a little bit so that we can pull the actual address back. Just gonna call it PC there. Cool. So I can't remember. Yeah, it looks like in digital I can't view the contents of this at runtime. But I can do it if I pause this. So if I edit this, I can go in and say put some values in here. So these values are like, this is machine code. Obviously this is just garbage right now. Why isn't it like that? It's kind of annoying that you have to type the 0x each time. Okay, so this is counting from 1 to 15 in hexadecimal. Cool. And then now that we've kind of ran past that address, which, let's see, that address is address E. So we should see, excuse my cat, he's trying to get up in my lap here. We should see that once we pass like address F, yep, we hit that, this went down to 0 here because the rest of the ROM is 0. So that's pretty cool. Now this is actually not entirely correct. So I mentioned that our memory is supposed to be 16 bits wide, and that also that we want it to be byte addressed, but with the ROM set up how it is here, it is 16 bits wide, but it's actually not byte addressed. It's word addressed because um, the values in these cells are 16 bits wide, which is not what we're wanting to see here. So, and if anyone in the comments has used digital before, let me know if there's a better way to go about this. But I'm actually going to basically have two different ROMs that are each going to store 8 bits. And we'll get we'll get 1 byte of the instruction from each of these. So I'll call that one high, and I'll call that one low. And then we'll put a splitter on here so that we can take 8 bits on our inputs, 2 of those, and then 16-bit output. And if you didn't know, in digital you can come in here, you can adjust the spreading of this, and it will actually basically just make this wider, which I think can make your circuit layouts like a little bit prettier. And then I think we just want to send the address to both of these. Is that 1 bit? That is 1 bit. Okay, what's going to happen here? Cool. So we're seeing the same behavior here. If I was using some really large values in here originally that didn't fit in 8 bits, then we would start to see some weird splicing, I think. But because I didn't do that, I think that's what I would expect to see. So that is that. So now we need to basically store this instruction value into a register, and that's going to be our instruction register. Now in a pipeline, you kind of have an instruction register in like every stage, really, because you're passing the instruction being executed forward, or if not the instruction, decoded control lines that represent that instruction. So you can think about this as, I guess, like the first pipeline latch that will slot in between the fetch stage, which is where the program counter lives, and the decode stage, which will go over here and represents or it'll be responsible for taking the instruction fetched from program memory and then turning it into control lines that orchestrate the ALU and the register file and the data memory and the write back and the next 4 or 3 stages in your classical pipeline. So I'm going to basically disconnect this over here. If you hit T, you can create this special little item in digital called a tunnel, which is like an invisible wire. So if I connect this tunnel right here, this is like equivalent to how I had it wired just a moment ago. But the benefit of that is I can, connect the tunnel over here as well, and now both this guy and this guy are going to get clocked, at the same time by the same signal, but I don't have to draw that signal like all the way through the circuit, which could get pretty messy. So I'm going to move that up here. We're going to store 16 bits here. We're going to call this the IR, the instruction register. I guess for consistency, we'll just do that. We'll go ahead and label this to denote what that is being used for. And then we'll probably want to start like collecting some values that we can put in like a little control panel just to kind of have like a diagnostic like readout of the state of the processor. So, well, I was gonna transform this one into the value of the program counter, but it might be nice actually to have the clock signal here. But then the next one will be the program counter. That value is 16 bits. Make a new tunnel. I don't want to rename it because this is a new tunnel. And I'm a bit OCD, or well, I don't want to overuse that term, but I'm a bit detail oriented. I kind of want this to look nice. So maybe we can rotate this like vertically. Scoot this back. Okay. And then we'll have another readout here, which is IR. Copy this, make another one. I'm on a trackpad, which accounts for a little bit of my clumsiness. Name that. And I'm going to say this is all right. So IF is instruction fetch, and ID is instruction decode. And then we're going to enable that. And let's see if it works still. It does, but let's make these small. See if this fixes the overlapping readouts up there. Not quite. So we'll just space them out. Yeah, so that's cool. I think that's just a decent start. You know, I've never made a video like this before, edited it, so I'm you know, I got to go figure out how to edit this and put it together, and that'll be a little bit less daunting if it's not like, you know, an hour long or something. But I'll just show y'all like another little trick here. Right now I have this start real-time clock checked, but if I tap that, you'll see now the clock isn't moving. It's up to me to clock it myself here. And then I think there's another thing we can do here. I think there's a way to... I thought there was a way to use like the spacebar or some key binding to... There we go, yeah, it's C. Okay, yeah, so instead of having to click this, I can just use C, which of course that would be really useful if we had a really big circuit and it wasn't even on screen. I could hit C like I'm doing right now. But other than that, that is the very initial work of our 16-bit pipelined CPU. I'm gonna get this edited up. Hopefully, you know, some of y'all find this interesting. And then in the next video, we'll probably put together some semblance of a register file and a write back so that we can come up with some machine code for moving values between registers. Something I want to try to do is have a pretty kind of vertical slice development style here, where at every step along the project we have something that does something, and doesn't just do nothing until the very end and everything is all put together, because that's how I naturally work, and it's not a very successful way to go about these things. So if you have any suggestions on how what kind of natural progressive steps could be made to achieve that goal, then let me know. But other than that, thanks for checking this out, and yeah, hopefully I'll start working on the next one pretty soon here.